Okay, thank you very much. Okay. So my name is Felix Minta from Egypt, Japan University of Science and Technology, and from the Department of Space Environment, and I am here to present my work on behalf of my team, forecasting the transit times of directed CMEs using artificial neural network, a case study application with GCS forward modeling technique. So thanks to Hashista and Ms. Hannah for taking the lead to present about tracking CME and also the use of GCS. So in a couple of minutes, we'll be looking at the background, as well as the objective, as well as data. Then we'll present some few results, and then we wrap up with the conclusion. So CMEs are actually, and they are associated ICMEs, are manifestations of magnetically driven plasma that liberates large amount of energetic particles when they transit from the sun into the IPM, and they typically take on an average of 1 to 5 days to be registered at the vicinity of the Earth, causing violent geomagnetic storms. And because of that, a lot of work has been done to predict their arrival time. But however, most of these models come with different level of complexity, and also some did not really take into consideration some certain physical conditions that hampers the performance of the model. Some also rely extensively on the 2D speed, like what Hashista has just presented. However, for such models, they typically have a mean absolute error of 10 hours. So, like I said, how complex the model is does not really guarantee how accurate it will be, but the ability of the model to capture certain heliophysical conditions like CME-CME interactions, as well as high space solar wind streams from coronal hosts, and also significant deflection of CMEs in the IPM and background solar wind, as well as the orientation of the BZ component. So our aim over here is to try to mitigate errors in tracking or predicting CME transit time that are prone to projection effect, and also look at how some of these parameters that we obtain from the GCS model can be used as proxy in terms of the initial speed and other parameters. So in brief, the data we use over here, we use the Forbish effect and the interplanetary disturbance database, as well as the near-Earth ICME list compiled by Richardson and Kane. So after checking for any form of discrepancies, we were able to check for ICME start time, as well as we were able to collect the solar wind speed. Then also we need to match the ICME-CME association. So therefore, we estimated the align time to be approximately 6 days, and also trace the event back to their sources, assuming that they transit radially on the line of sight and also does not experience any significant deflection. So we saw this to be very close with the CME event that has been provided by Richardson and Kane. So therefore, we collected the large time elastic field of view, and then we also took their heliographic sources as well as the space speed over here, which is also estimated using a cone model. Then with the space speed and the heliographic sources, we were able to use the empirical equation proposed by Gopaswamy in 2013 to estimate the earthward speed. So with the earthward speed, the space speed, and the solar wind speed, they are not speed that are really influenced by projection effect, and we propose or we assume that they are the true speed of the CME, and therefore they do not have any significant influence due to projection effect. Also, aside the fact that we are also interested in mitigating projection effect, we also need to take into consideration certain criteria or certain condition that also hampers the performance of the model. So we ensure that there is no, all the data or the data repositories have different ICME, CMEs, start and onset and set of times. And also, so we ensure that for in the case where there is ambiguity in the data, we discard such events, and also we ensure that the ICM-CME must be geo-effective, where in this case, we look at drastic depression in DST index and to be on the order of negative 30 nanotesla and below. Then also, we also ensure that the CME must be declared as partial or full halo, in this case where partial has an angular weight greater than 120 degrees and the full halo is 360 degrees. And of course, they must be facing the Earth, or their source region must originate from the Earth. And also, we also take into consideration CME-CME interaction. So running images review also help us to discard events that are actually having issues of CME-CME interaction, and also review from the extreme ultraviolet contemporary data from atmospheric imaging assembly also help us to discard high-speed solar wind streams from corona hosts that are interacting with associated CMEs. So this is a typical example over here. So the CME that we saw over here has been seen in both stereo and LASCO as halo event. And also, we saw that it associated ICMA, which marks the arrival of the shock, was registered around 3rd to 5th November 2021. And also, when you look at the true signatures of the ICMA, we saw rotation in BZ component and enhancement in the total magnetic field, as well as enhancement in the solar wind speed. On the other hand, we saw plasma temperature and plasma beta being significantly very low. This actually classified the HCMA to be a typical magnetic cloud. And we saw also a depression in DST index that shows that this particular HCMA is geo-effective. So then we deployed the cascade forward neural network over here where we randomize our data into 70% for training, and we reserve the 30% for testing and validation purposes. So our neural network take into consideration, let me say, the true speed over here, which is the space speed, the earthward speed, and the solar wind speed. Then we deploy the Levenberg algorithm that is proposed to be first choice algorithm and also considered to be fast. So during the trial and error process, because machine learning is actually a trial and error process, it does not have any specific formula. So varying series of number of neurons and hidden layers, we're able to get the architecture of 3 hidden layers that comprises traces 4 neurons. So in the first hidden layer, it has 3 neurons. In the second has 6, and that has 4. Then also, yeah, like I said, so the Levenberg take into consideration the Jacobian rule that helps to systematically adjust network weights to avoid or minimize overfitting or underfitting, and also has the gradient descent function that helps to minimize cost function as well as speeding up the training process. Then we use the log sigmoid in as our transfer function. So during the training, we continuously monitored our validation error, and we saw that the error significantly, sorry. All right. We saw the error decreasing and then drastically converge at the 28th epoch. So at that point, the network the training was considered complete and therefore automatically terminated. However, we were faced by limited data because our data over here is just 290 set, and we also saw some correlation between input and target. However, because the cascade forward neural network has the ability to accommodate non-linearity and also retain the linearity, we're able to curtail and prevent this error from growing. So results quickly. We predicted a transit time of 87 CMEs, and we had a mean absolute error that is expressed in the red line, where about 7.3 hours. However, we saw that most of the event that we predicted lies close to the black line. This indicates that subsequent predictions can actually be achieved to have a mean absolute error hovering over this one. We saw that our prediction was significant or close to the observed, where it is on the order of 1 to 5 days as against the observed, which is 6 days. So in this case, we use the GCS over here, where we wanted to use parameters from the GCS as proxy. So we perform fading for 5 set of events as a case study, and we then get the 3D speed over here, which we saw it to be around 10, 18 kilometers per second as against the 2D speed over here that is significantly higher than the 2D speed. Probably the 2D speed must be underestimated. We also take into consideration certain uncertainty in order to achieve, because the GCS relies on assumptions, so we took into consideration the assumptions that it must exhibit self-similar expansion and transit radially and also experience no significant deflection. So we look at the speed profile with the 2D speed and the 3D speed as well as the space speed, and we saw that they are really or nearly consistent with the mean hovering around 1,000 over here. Therefore, we need to also support our hypothesis. So we pick a 3D speed that has been estimated from two papers, about 41 events, and we then correlate it. We saw a significant correlation between the 3D speed and the space speed over here. And also we perform a student test that gives us a probability that is 0.01, which is less than the critical value over here. So then we use the drag-based model to also, we want to compare our result with the drag-based model, other state-of-art models. And we saw a significant approximation of the transit time with the drag-based model. Then we compare that with the ESA, which has been proposed by Gopaswamy et al. And we saw that our neural network gave us a mean absolute error of 5.2 hours, and the ESA gave 13 hours, and the DBM gave 6. So in this case, our model and that of the DBM gave a close consistency. However, the ESA seems to exhibit some flaws over here. So now, in this case, we saw that why the ESA performed poorly is due to the fact that on the 7th December event, we saw that the event is a complex ejector over here, and it has been preceded by 7-week event on the order of 47 hours. This increased the effective draft, and because the ESA has been premised on the idea that it must be shock-driven, and because this one is a complex ejector, it does not take into consideration the heliophysical condition of this particular event. Then in this case, here we run our model again using the GCS, because we were able to establish that the 3D speed is the same as the space speed over here, and we saw our mean absolute error again dropping to 4.5, which is close to that of the space speed. In that case, we propose that in the absence of the space speed, we can use the 3D speed as a proxy to simulate our model. When we look at the deviation, we saw our model deviating on the order of 0.2 to 8 hours, and that of the ESA on 24 hours, and the DBM on 13 hours. So in conclusion, we implemented a machine learning model that is devoid of errors due to projection effect, and also we saw a significant agreement with other state-of-art models. And our study also emphasized the efficiency of the forward modeling technique in studying 3D kinematics of the CME, and also highlight the essence of utilizing deep projected parameters in improving CME transit time forecasting models. And also, if the space speed or the solar wind speed as well as the drag parameter is not underestimated, you can equally use the DBM to predict shock arrival times. Thank you.
Thank you very much. Thank you. Do we have questions?
Okay. Just to clarify, you first did the reconstruction, and then you fed it into the machine learning model of your events.
Yeah, because our model takes into account the inputs to our model are the 3D speed, or let me say the space speed, and the H2O speed and the solar wind speed. So we did a reconstruction to obtain the 3D speed, and then we feed it into our model.
And you did that on these 87 events?
No, because our 87 event has been randomly selected by the code. So if we said we will perform 3D reconstruction on the 87 set, probably we are not going to achieve it due to the fact that the GCS relies on multi-view observation. And because we are tracking the event from SOHO and that of stereo, we will definitely have a deficit where there will not be stereo observation on one particular set of events. So here we use the space speed that has been computed by a code model to train the model. And now we hypothesize that, okay, in the absence of the space speed, we can use the 3D speed. So the 3D speed over here, we are just using for a case study purposes, where we reconstructed for 5 selected events, then we use it as input, yeah.
Any more questions? Yes, please.
And you mentioned that you didn't take into account the deflection of the CMEs. So are you considering
Okay.
to?
I said in my previous slide that for the event that we considered, we make sure that they do not exhibit some level of deflection.
Ah, okay.
Yes.
All right. Any questions? If not, then thank you very much.
Thank you very much.